Now that we have developed our reliable data transfer protocol, RDT3, let's see what would be the performance of our protocol and what improvements can be done to improve that performance. In this, we'll discuss two different strategies, one known as go backend and another known as selective repeat. Our RDT3 protocol is a functionally correct protocol. It achieves the major requirement. What was the major requirement? To achieve reliability working over an unreliable medium. That it achieves very correctly. So functionally, it's a very correct protocol. But there is a certain problem. What the problem is? The problem is that at a particular point of time, only one packet is flowing over the network. See, so this is a sender and this is the receiver. Now if you remember the operation of our RDT protocol, you should understand that the sender sends a packet and then it waits for the acknowledgement. So it sends a packet with a particular sequence number, then it waits for an acknowledgement. That means during this period it has sent only a single packet and now it is waiting for the acknowledgement. Once an acknowledgement arrives, it can send the subsequent packet or it can retransmit depending on what was there in the acknowledgement. So in the network at the time only one packet is flowing either in this side from the sender to the receiver or from the other side from the receiver to the sender, either a packet or an acknowledgement. That means a single packet is flowing in the network at a point of time. So you can understand what can be the performance of this particular protocol. A single packet flowing over the network at one point in time, and what can be that what can be the efficiency of the network. You can simply understand it would vary. What type of efficiency? We cannot have a network with such type of protocol. Imagine two computers connected with each other in the different parts of the world through a very high speed network, say with a high speed transmission rate of 1 Gbps, and if using a transmission rate of 1 Gbps I am sending only one packet at a time, then you can understand there is no use of using that high speed transmission rate. It will simply be useless. Only one packet is flowing. So basically the problem with a stop in wait protocol, the RDT 3.0 is a stop in wait protocol. It sends a packet and it stops sending further packets until and unless it gets an acknowledgement. If it gets an acknowledgement, it then sends a subsequent packet. So this stop and wait protocol cannot be turned as a performer in a network. A protocol where only a single packet is there in the pipeline, we cannot invariably use it in the world of networking. So what do we want? We want that many packets should be able to be sent from the sender to the receiver. Instead of one packet, I should be able to send more packets. So essentially I require a strategy which allows me to send more than one packets. That means having more than a single packet in the pipeline instead of having one single packet. Now one question may arise is that why not send all the packets? If data has come from the application layer and send, say 1000 packets have been created from the data, why not send the 1000 packets at the same time? Instead of sending one packet or two packet or 10 packets or 15 packets, why not send all the 1000 packets? The reason is that there are two issues which we'll discuss subsequently. One issue is known as flow control and one issue known as congestion control. For these two reasons, we cannot send any arbitrary number of packets over the network. We have to decide how many packets we can send at a particular point of time. Now remember, in the stop and wait RDT3 protocol, we can send only one packet. We send one packet and we wait for the acknowledgement. That means at a point of time in the pipeline, there is only one packet. When we send one packet at a time, we say that this is a stop and wait protocol. But when we send multiple packets at a time, that means obviously now we have to change our strategy. Because we are sending multiple number of packets, obviously how I'm going to handle loss of packets, how I'm going to handle the acknowledgement of those packets, these things I have to change in my protocol which I have developed. Now, what would be the requirements of such a protocol? Can you think about it? What would be the changed requirements where I'm able to send more than one number of packets? the protocols where I am capable of sending more than one packets, these are known as pipeline protocols. Instead of a stop and wait protocol where I can send only one packet, pipeline protocols allow me to send some more amount of packets. So in pipeline protocols, the sender is allowed to send multiple number of packets without waiting for their acknowledgments. We'll see how what type of strategies can be adopted. Now, first thing, the question was what changes will be required. The first requirement is obviously the number of sequence numbers should be increased. Remember, in our stop and wait protocol, only two sequence number was required, 0 and 1, because two sequence number was sufficient to delineate the different packets. But since now we are sending more than one packets, that's why we require more sequence numbers. The other thing is we require buffering. Remember, we have to retransmit lost packets. Now, because we are sending more number of packets, so until and unless the sender is sure that those packets have arrived correctly at the end, it should store them and if required, they has to be retransmitted. So now I require a buffer space, more buffer space. At the time, I had to store only one single packet. I'm sending a single packet till the time I receive the acknowledgement, I require to store it. Now, because I have now sent a number of packets, I have to store those packets. Theoretically, I have to store all those packets until and unless I receive an acknowledgement for those packets. Only when I receive an acknowledgement that the packet has been correctly delivered at the other end, I can remove it from the buffer. So the other requirement is having buffer space both at the sender and the receiver side. Essentially now we have pipeline protocols which allows me to send more than one packets at a point of time without waiting for their acknowledgement. And due to this, we require more sequence numbers and more buffering. And there are two different types of pipeline protocols which are used in networking. One is known as go back N and another is known as selective repeat. So today we'll discuss these two strategies, go back N and selective repeat. So let's first discuss this protocol known as go back N. Go back N and is popularly known as GBN. G stands for go, B for back. And this particular parameter known which we have denoted as N. Let's discuss first what this N stands for. This N stands for the number of packets which we can send at the same point of time. That means when we use stop and wait protocol, we can send only one packet. But when I say go back N, this indicates the number of packets we can send simultaneously. That means if the N is say 4, then I'm capable of sending 4 packets simultaneously. In stop and wait, I could send only one packet. In go back N, if N is 4, I'm capable of sending 4 packets. If N is 10, I'm capable of sending 10 packets at the same time. If N is 100, I'm capable of sending 100 packets at the simultaneously. Remember, I can send 100 packets if only I have 100 packets available with me. Remember that. That means I have a continuous stream of data coming from my application layer. If there are not 100 packets available, obviously I will not be sending 100 packets at the same time. Having capability of sending 100 packets does not mean that data is always ready. It simply means that at any point of time simultaneously I'm capable of sending 100 packets if N is 100, if 100 packets are available with me. Now, why do we choose a particular number, 4 or 10 or 100 or 15 or 50 or 1000, anything? Why not all the packets? This we have just discussed because there is something known as flow control and congestion control. This we will discuss subsequently in a subsequent lecture what this flow control or what congestion control is. But remember, we select an N and whatever N we select, we are capable of sending that N number of packets. Now, why we say go back N? Now, let's discuss this strategy. Why do we call it as go back N? Now, let's try to understand this strategy known as go back N. Now, when we discuss, again, there is two sides. One is known as the sender side and another known side is the receiver side. Now, the first concept we should understand in this strategy is that there is something known as window size. Window size. Now, the window size of the sender is N, whatever N we have decided. That means what does window size indicate? The window size indicate the number of packets which we can send simultaneously, one after another. That means if n is say 10, we are capable of sending 10 packets without waiting for acknowledgments at a time. Now, for the sender side, the window size is n, whatever n we have decided. In go back n, the receiver side window size is always 1. Now, this is an important concept. In the receiver side, the window size in go back n is always 1. The sender side, the window size is n, and which we have decided, but in the receiver side, the window size is 1. That means the receiver always waits to receive one single packet at that time. And listen to this very carefully. The receiver waits to receive only one packet at a time, and it expects the packet to be coming in order. That means, say if I'm sending 10 packets from the sender side, and say the sequence numbers are simply like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The receiver side window size is 1. That means at the first instant it is waiting for packet number 1. Once it receives the packet, it is waiting for receiving packet number 2. It has received correctly. Now it's waiting for packet number 3. If it does not receive packet number 3 and say it receives packet number 4, that means it is not receiving a packet in order, it is receiving a packet out of order, and go back n does not receive any packet out of order. It will only receive those packets which has arrived in order. Now this is the very important concept. Again, the concept is that the sender is capable of sending n number of packets at a time without waiting for their acknowledgement to come. That means it is not like that the sender is sending, if say n is 5, it is not something like it sends packet 1 and is waiting for acknowledgement. It is sending packet 2 and waiting for acknowledgement. If the window size is 5, n is 5, that means it will send 5 packets without waiting for acknowledgement. Now after sending 5 packets, it will wait for acknowledgement to arrive. Once it acknowledgement arrive, how does it behave? We'll see subsequently. At the receiver side, it is only waiting for one packet at a time, and that packet should be in order. If it is waiting for packet number 1, it should receive packet number 1. If it is waiting for packet number 2, it will send acknowledgement for packet number 2. It will receive packet number 2. If it receives a packet out of order, it will simply discard it. It will not send an acknowledgement for that discarded packet. It will send only an acknowledgement for the last correctly received packet, which we have discussed in RDT3. And it will discard the previous packets. Now let's see how this go back n protocol operates. Now let us understand the operation of this go back n protocol. Now let's assume that a sender is sending some packets to the other side, and it has selected n equal to 3. That means it is capable of sending 3 packets at a time without waiting for their acknowledgement. Now the window size is 3, n is equal to 3. Now say this is the sender side, this is the receiver side, and because we can now use many sequence numbers, so let's say I have a host number of sequence numbers available. Starting from 0, the sequence numbers increase by 0, 1, 2, 3, 4, 5, 6, 7, like this. I can use this sequence number, but essentially we'll later see that the sequence numbers are reusable. At some other point of time, we can reuse those sequence packets, as in RDT3, where we could use the sequence number 0 and 1 repeatedly, one after the another. But as of now, assume that these are the sequence numbers, and also assume that all these packets are available at this point. That means data is available. These packets have been created and these packets are waiting for transmission. Now because n is equal to 3, I am capable of sending 3 packets at the same point of time. So say from the sender side, I have sent 3 packets. What would be these 3 figures now? 0, 1 and 2. So I can send 3 packets one after the another without waiting for their acknowledgement. So I have packet with sequence number 0, sequence number 1 and sequence number 2. Those 3 packets I have sent. So the window size is 3, and is 3 for the sender side. Though I have other packets ready, I have packet 3 with sequence number 3 is ready, 4 is ready, 5 is ready, but because n is equal to 3, I can only send 3 packets at a time. At the other end, the window size is only 1. Remember, we have just mentioned that the window size at the receiver end is 1. It is always 1 in go back end. Now let's see. So first it is the receiver is waiting for packet number 0. It will receive only packet in order. So say packet number 0 arrives. So this it has correctly received packet 0. Now it will send an acknowledgement for packet number 0. So 0 packet has arrived and it has sent an acknowledgement for packet number 0. Now as soon as after 0 it also send packet 1, packet 2. Remember, without waiting for an acknowledgement it can send all these packets. So 0 it sends 0, 1 and 2 one after another. Now after some point of time it has received the acknowledgement for packet number 0. So one packet has been acknowledged. Now it can send one more packet. That means this window because it has received an acknowledgement packet number 0, one more slot has become free, because at one point of time 3 packets can be in the pipeline from the sender side. Because it has received an acknowledgement, now there are only 2 packets which are unacknowledged. Packet number 0 has already been acknowledged. It has sent 1 and 2. It is waiting for an acknowledgement. Now one slot is free because n is 3. Now it can second packet with the sequence number 3. It looks as if this window has slided. It was there for 0, 1 and 2. Now the window has slided for 1, 2 and 3. That's why these protocols, these type of protocols are also known as sliding window protocol, because it is as if the window has slided. Now it has also sent packet number 3. Which sequence number 3? It is the 4th packet. Now it is waiting for acknowledgement of packet number 1, 2 and 3. Now after some time, when it's the receiver side, after receiving packet number 0, it is waiting for packet number 1. Now say it has received packet number 1 correctly. Now it sends an acknowledgement for packet number 1. As soon as the sender received the acknowledgement for packet number 1, now this particular window has slide again. Now because 3 packets can be there in the pipeline, 2 packets have been already acknowledged, 0 was already acknowledged. Now what has been acknowledged? Now 2 and 3 are there in the pipeline. Now it can send one more packet. So now say it has sent packet number 4 also. Now the receiver has received packet number 0 correctly. It has received packet number 1 correctly. Now it is waiting for packet with sequence number 2. Now say this packet number 2 was lost. Now this packet number 2 which was sent was lost. Now it is waiting for packet number 2. The receiver is waiting for the packet number 2. But packet number 2 is lost. Now after some time packet number 3 has arrived. Now remember, the receiver does not receive any packet out of order. It will receive packets with the correct sequence number only. So it will simply discard packet number 3. And this is one of the reasons why the receiver side has always gotten window size of 1, because it is only receiving packets in order. It will not receive packets out of order. That's why it requires to have only one window. Now it is, because it was waiting for packet number 2, it received packet number 3. It will simply discard packet number 3 and it will send an acknowledgement for the previously correctly received packet. Now 2 things can happen at the sender side. It may happen that the timer of packet number 2 has timed out. Remember, the sender will start a timer for each of this packet. It will start a timer for packet number 1, packet number 2, packet number 3. For each of this packet, it will start a timer, as we have discussed in the RDP 3.0 protocol. So the first thing it can happen that the timeout for the packet with sequence number 2, it has timed out. It is waiting for an acknowledgement from the other side, but the packet has got lost. Now because the packet has got lost, it is not receiving an acknowledgement and it has timed out. Now this part is very important. Now because it has timed out, it will assume that the packet must have got lost in transit. Now because it also means that even if the other side might have received the other packets, it might have received packet number 3, it might have received packet number 4, but because the receiver window is only one, that means it has not received those packets in its buffer. That means it has discarded those packets. That's why now it will retransmit all the packets starting from sequence number 2. That means the sender side was waiting for an acknowledgement for packet number 2. It did not receive an acknowledgement for packet number 2. The timer timed out. Now it will go back, the window will go back to the sequence number 2 and it will send all the packets starting from sequence number 2. That means it will send packet number 2, packet number 3, sequence number 2, sequence number 3, sequence number 4 again, though it has already sent. So it will not wait for any information about the packet number 3 and 4 which it has already sent. Because the timer of 2 has timed out, it will immediately resend packets starting from 2, because it goes back sending of data packets from the point where it did not receive an acknowledgement. That's why it is known as go back n. That means it go back to n number of packets from when, till it received that unacknowledgement packet. It did not receive acknowledgement for packet number 2. That's why it went back, it slide back the window starting from 2, and then it starts sending again packet starting from sequence number 2. So it will start again sending packet 2, 3, 4. Because again n is equal to 3, it will send 3 packets. Because it resends all the packets from the point where it did not receive an acknowledgement, that's why it is known as go back, and it go back to that point where it did not receive an acknowledgement. The other thing it can happen that before in timeout it received the duplicate acknowledgement for packet number 1. Remember, when the receiver side received packet number 3 out of order, when it received packet number 3 out of order, it was waiting for packet number 2, it received the packet 3. What it would do, it will send an acknowledgement for the previously correctly received packet, it is for the packet number 1. So when it sends the acknowledgement for packet number 1, the other side, the sender side, if it receives the acknowledgement for packet number 1 again, that means it has received a duplicate acknowledgement. It again understands that it has lost probably it has lost the packet number 2. The action will be similar. It will go back from sending the packet with sequence number 2. So this is how go back and operates. Now let's see this particular protocol using an animation, which should be even more clear for you. Now we'll see an interactive animations of the go back and protocol. This animation should be able to clear any doubts you are having about the working of go back and. Because this animation is built in a programming language, sometimes things may be slower regarding timeouts, and also be patient with that. Now this is the animation window, and let's assume that this is the sender side, this is the sender side view, and this is the receiver side view. And let's assume that n is 5 for the sender side. So at the same time it should be able to send 5 packets at the same time without waiting for an acknowledgement. The window size of the receiver is always 1. If you look at it, window is shown, so the window size of the receiver is always 1. Let's assume that the window size is 5. Now if I have data available, I should be able to send 5 packets at the same point of time. First, let's see how it works in the regular thing. How the go back and works. If everything is correct, there is no loss of packet, there is no loss of acknowledgement, nothing like that. If nothing error occurs, how go back and works. So let's say I have data available, data is coming from me. So say these 5 packets can be sent. So if I have new packets, I cannot send now. Now let's pause for a moment. So 5 packets with sequence number 0, 1, 2, 3, 4 were sent. The receiver received them correctly. So when 0 was received, it sent an acknowledgement for packet number 0. When 1 was received, it sent an acknowledgement for packet number 1. When 2 was received, it sent an acknowledgement for packet number 2. And then if you see, it was waiting for packet 0, it correctly received, and it went here, it was waiting for packet number 1. So the window of the receiver side is sliding. If you look at it now, the windows is here. That means it is now waiting for packet number 5. if packet number 5 arrives correctly, then it will receive it. Now it has sent this acknowledgement. Let's resume our animation. Now see, let's see what happened. So once this is received, the acknowledgement for 0 is received at the sender side, the window will slide. That means one more slot will open up. Let's see. So one more slot is open up, so I can now send further packets. So I hope the normal working is clear for you. Let's see the normal working again. Let's see how the window is sliding. See, so this window is sliding. As soon as it receives an acknowledgement, the window slides. Now we'll see a situation where there will maybe loss of packets. Now let us see what will happen if packet get lost while transmitted from the sender to the other end. Say we have these 5 packets being sent. Now let's assume that this packet number 3 gets lost. Let's kill this packet. That means this packet will get lost during transmission. Now let's see how the receiver will behave. Now receiver first, it is waiting for packet number 0. Once packet number 0 arrives, it will send an acknowledgement for packet number 0. Then it receives packet number 1, it sends an acknowledgement for packet number 1. It receives packet 2, it sends an acknowledgement for packet 2. Now it is waiting for packet number 3. Now it did not receive packet number 3 because it got lost. It received packet number 4. Now remember, go back and the receiver side will not receive packets out of order because it was waiting for packet number 3 but it received packet number 4. It will not receive packet number 4, it will simply discard this packet, and what it will do, it will send an acknowledgement for the previously correctly received packet. What is the previously correctly received packet? It was packet number 2. So at this point of time, it will send an acknowledgement for packet number 2. Let's resume our operation. Let's see. You see here. So for 0, it sent a 0 acknowledgement. For 1, it sent an acknowledgement for packet number 1. For packet number 2, it sent an acknowledgement. 3 was lost. When 4 was received, that packet was discarded. And it sent an acknowledgement for packet number 2 only. So now concentrate on the sender side. What it will do once it starts receiving the acknowledgement. So let's see. It received acknowledgement for packet number 0. Once it received packet number 0, it slides. Now the packet has slid till here. So if I have new data, I will be able to send this data. Now let's see what happens here. Now it was waiting for acknowledgement for packet number 3, but it has not received acknowledgement of packet number 3 because it was lost. Now for packet number 4, it discarded, and then a acknowledgement for packet number 2 was sent here. Clear? Now what happened? After a few moments, timeout occurred. Which timeout occurred? Timeout for packet number 3. Now it understood that the packet number 3 did not arrive, so it starts sending packet number 3 starting from packet number 3. That means packets, it will start sending packets from the sequence number 3. It would again send packet on sequence number 4 also. That means starting from 3, it will start sending all the packets that were sent previously, immaterial whether those other packets were received or not. Remember, because it received packet number 4 but it did not buffer that packet, it simply discarded or rejected that packet. So essentially go back and means it will go back from that point where it did not receive an acknowledgement, and from that point onwards it will send all those packets which were there. So I hope this should be clear. What is the meaning of go back? And it's going back to that point from where the acknowledgement was not received. So this will now continue. So if I have new packets, I can always send those packets. Now this would be correctly acknowledged. Now the window can slide. Clear? Let's see a few more examples. I have this. Say this packet got lost. Let's resume. So I am now sending these packets. Now remember, it will not receive packets out of order. So it is sending acknowledgement for the previously correctly received packets. See? Now see, the window is not sliding. because it is waiting for an acknowledgement for packet number 12, but it is not received the acknowledgement for packet number 12 because this packet number 12 was lost. It received all these packets correctly the other side, but because they were received out of order, it did not. Now after timeout it will send all the packets starting from sequence number 12. Clear? So I guess this should remove all your doubts. So this is how go back AND protocol works. Now there is an interesting situation. What if an acknowledgement get lost? Say the packets were received correctly from the sender, but a subsequent acknowledgement got lost. What would be the viewpoint of the sender when certain acknowledgement got lost and they received a different acknowledgement? Let's understand with an example. Say the sender is sending 5 packets. These packets have been received correctly, the acknowledgement are being sent, and say by some way or manner this particular acknowledgement got lost. Correct? The acknowledgement for packet number 2 got lost. Now let's resume it. So one should be clear. One, the packet number 1, which has sequence number 0, it received correctly. Now let's think of it, what will happen now. So 0 and 1 sequence number it has received correctly. So this window has slide. Now it did not receive the acknowledgement of packet number 2. It was received correctly at the other end, but the acknowledgement was lost. Now 3 was received. Because it received 3 correctly, it will send an acknowledgement for packet number 3. Remember, if a packet was lost, then it will send an acknowledgement for a previously correctly received packet. Now, but because it has received the packets correctly in order, it will send the acknowledgement in the correct order. Now, the sender is waiting for an acknowledgement of packet number 2, but it will receive an acknowledgement for packet number 3. Now, should it slide the window or it should not slide? Will it again send this packet from the sequence number 2? Think of it. What should this go back AND protocol sender side do now? Should it again send from all the packets starting from 2 because it did not receive the acknowledgement for packet number 2? Now you should convince yourself that if it receives a packet with a particular sequence number, that means it should understand that all the packets prior to that particular packet was correctly received at the other end, irrespective of whether it received this acknowledgement for that packet or not. If it sounds confusing, let's understand it in some other way. Let's see. Say the window size is 4 and it has sent this packet 0, 1, 2, 3. The window size is 4, it has sent these packets correctly. These packets were correctly received at the other end. 0 packet was received, it sent acknowledgement for packet 0, then 1, then 2, then 3. By some chance, acknowledgement for packet 0 was lost, even 1 was lost, even 2 was lost. 3 acknowledgement got lost, and the senders received only packet number acknowledgement for packet number 3. Now what it should do? Now this is very interesting. If the sender receives the acknowledgement for packet number 3, it did not receive the acknowledgement for packet number 0, 1 and 2 because they were lost, the sender should understand that the receiver would send acknowledgement for packet number 3 only if it had received all the previous packets correctly. It is sending an acknowledgement for packet number 3 because it has received packet number 0 also, it has received packet number 1 also, it has received packet number 2 also. That's why it has sent an acknowledgement for packet number 3. Otherwise, it would have never sent an acknowledgement for packet number 3 if those packets were lost. That means if the sender receive an acknowledgement, say it is received the acknowledgement for packet number 3 only, the acknowledgement for the other 3 packets were lost, even then the sender will understand clearly that the packets were delivered correctly. 0, 1 and 2 was delivered correctly because it has received an acknowledgement for packet number 3. That means If the sender receive an acknowledgement, it simply means that all the previous packets prior to that acknowledgement was also correctly received, irrespective of whether it received those acknowledgements or not. And this is a very important characteristic of Go backend, and this is known as cumulative acknowledgement. Cumulative acknowledgement. That means Go backend understands something known as cumulative acknowledgements. You should convince yourself that you have understood this aspect of Go backend. So Go backend uses this concept of cumulative acknowledgement. So cumulative acknowledgement, it indicates that an acknowledgement for packet number k, indicates that all the packets before k were delivered correctly, whether the acknowledgement of those previous packets were received by the sender or not. Again, that means if I receive an acknowledgement for packet number 6, it means that all the previous packets number 0, 1, 2, 3, 4, 5 were also received correctly, because only then it was able to send the acknowledgement for packet number 6. Now this cumulative acknowledgement can in fact be worked in strategy also. Instead of sending an acknowledgement for each and every packet, Go back and can decide to send acknowledgement for a particular sequence number. Say the window size is 10, and it will send a cumulative acknowledgement. Instead of sending an acknowledgement for packet number 0, 1, 2, 3, 4 like that, say after every 5 packets, it sends a cumulative acknowledgement for packet number 5. Say it did not send an acknowledgement for packet number 0, 1, 2, 3. It sends simply an acknowledgement for packet number 5. It simply indicates that all the packets prior to packet number 5 were also correctly delivered. So Go back and can follow both the strategy using individual acknowledgement as well as cumulative acknowledgement. So this concludes the discussion on Go backend. So what is the essence of Go backend? The essence of Go backend is that the sender can send n number of packets simultaneously. The receiver, the window size of the receiver is 1. It receives packets only in order. It discards packets which were received out of order. Each time an acknowledgement or a packet is correctly received, the sender will slice its window so that more packets can be sent using that size of window. And if a packet is received out of order at the receiver side, it will discard the out of received packet. It will send an acknowledgement for the previously correctly received packet. And when the sender receives an acknowledgement which it was not intending to receive, that means it receives a duplicate acknowledgement or a timeout occurs, it will resend all those packets starting from that sequence number from where it did not receive an acknowledgement. So this is the essence of Go backend. Go backend also follows this strategy known as cumulative acknowledgement. Now we'll discuss selective repeat strategy. Now let us look at the other strategy known as selective repeat. The name itself indicates that it repeats selectively only those packets which were not correctly delivered. So in Go backend, all the packets starting from that point where acknowledgement was not received was delivered again, was sent again, but in selective repeat only those packets are retransmitted which were not delivered. Clear? So the first thing is that the window size of the sender side and the receiver side is same. So if the window size of the sender side is n, the window size of the receiver side is also n. In Go backend, it was if n is the sender side window size, the receiver side window size is always 1. But in this case, in selective repeat, the window size of both the sender and receiver is same. So if n is 5 for the sender, and the receiver side window size is also will be 5. The difference between Go back and selective is that when selective repeat starts sending packets, say the window size n is say 4 and the window size of receiver is also 4, so 4 packets will be sent from the sender side. Now each of these packets will be individually acknowledged. So for the packet number 0 it will be acknowledged, for packet number 1 it will be acknowledged. Say packet number 2 was lost. Now when packet number 3 arrives, the receiver will now not discard that packet. It will instead buffer that packet. It will store that packet and then it will acknowledge that particular packet. So it will send an acknowledgement for packet number 3. Instead of discussing like that, let's see the animation for selective repeat. That will make things much more easier for you. Now this is a demo animation of selective repeat. Now remember, the idea of selective repeat is that selectively repeat only those packets which were lost. Instead of sending a whole bunch of packets starting from one point, it selectively sends only those packets which were not acknowledged. Now first thing is, the window size of both the sender and receiver are same. Now it is same because here the receiver receives packets out of order. It will keep those packets in its buffer, and when all the packets arrive correctly after some point of time, it will slice its window. Let's see. So 5 packets are sent. Let's first see the normal operation. The normal operation is as in the go backend. So everything will be correctly acknowledged and then the window will slide. Now say let's look at a situation where a packet got lost. So say the packet number 7 got lost. Okay, so 5, 6, 7, 8, 9, 5 and 6 is correctly coming, 8 and 9 is also correctly coming. The packet number 7 got lost. Let's see how the receiver will behave. Now look at it. Packet 5 arrived, it acknowledged packet 5. Packet number 6 arrived, it acknowledged packet number 6. 7 not arrived, 8 arrived. It acknowledged packet number 8. The first difference will go back n. Go back n would have discarded this packet. It will not discard packet number 8. It is keeping packet number 8 in its buffer, and it has acknowledged packet number 8. Go back n would have acknowledged the previously correctly received packet. It received packet number 9. It acknowledged packet number 9, but it has not received packet number 7. It is still waiting. So let's go back to the sender side. So sender received the acknowledgement. Now let's see. If new packets arrive, these new packets can be sent, but it is still waiting for this old packets. These packets has been correctly acknowledged, but the window cannot slide until and unless this packets is correctly acknowledged. Now this packet was get lost. This packets has been correctly received. Now after some time, the timeout for this packet will happen. Because this packet was not correctly received, it was lost. Now time has occurred. Now this 7 number packet. Let's wait and see. So only one packet is sent. What happened in go backend? It would have sent all these packets starting from point this sequence number 7, 8, 9, 10, 11. All packets would have been resent in go backend. But here it is not resent. Only packet with sequence number 7 is being sent. The other packets have been buffered or stored at the receiver side. Now once it receives this packet correctly, now it will send an acknowledgement for packet number 7. This window has already been slided. Now this window will slide. Now further packets can be sent. I hope this operation is clear. In selective repeat, only that packet is reset which was not correctly received or which was lost. The other packets are buffered. Now cumulative acknowledgement will not work in selective repeat. When it receives an acknowledgement for a particular packet, it is only acknowledgement for that packet only. So if the original sender receives an acknowledgement for packet number 8, that means it is the acknowledgement for packet number 8 only. It does not indicate acknowledgement for the previous packet, because the previous packet might have got lost. Here only each individual packets are acknowledged. So cumulative acknowledgement does not work. The other fact here is that if acknowledgement got lost, the sender has no idea about it. So if acknowledgement is got lost here, even if the packet was correctly received, that packet has to be retransmitted. I hope you have got this. Let's see what does it mean. So these packets were sent. All packets have been correctly received. All packets have been correctly acknowledged. Say this packet number 2, this acknowledgement got lost, though the packet was correctly received. This packet was correctly received. Fine. So this acknowledgement has been received at the end. Now it is waiting for the acknowledgement of packet number 2. New packets can be sent. They will be correctly acknowledged. Now packet 2 was correctly received and correctly acknowledgement, but the acknowledgement got lost. In go backend, a subsequent acknowledgement number would have sufficient to indicate the previous packet was correctly delivered. But here individual acknowledgements are sent. individual acknowledgments are interpreted by the sender. So if an acknowledgement got lost, it has to be retransmitted. So after some timeout occurs, it has been retransmitted. Now this packet was already received, so there is no problem. So it sends an acknowledgement again. Once the acknowledgement arrives, now this window slides. So this is one situation which is very different from go back and. So essentially now you can understand that go back and selective repeat both have their own advantages and disadvantages. The advantage of go back end is very simple to implement. At least in the receiver side, you have only one single window size and you need not require to keep buffers, and then you do not receive packets out of order. That's why the implementation is simpler. The disadvantage of go back end is that if a packet got lost and if your window size is huge, then you have to unnecessarily retransmit a huge number of packets. Say your n is 1000 and you have sent 1000 number of packets and packet number 3 got lost and other packets were correctly delivered. What would happen? You have to retransmit starting from packet number 3 to that sequence number 1000. So it's a huge number of retransmissions. Unnecessary retransmission can occur. Advantages, you have already seen the simpler. Under advantages, it uses the concept of cumulative acknowledgement. Selective repeat. Advantage is you do not have to send unnecessary retransmission. Only you require to retransmit that particular packet, which was got lost. You need not retransmit all other packets starting from that packet. The disadvantage, if acknowledgement got lost, you have to retransmit, irrespective of whether that particular packet was correctly delivered or not. So trade-offs are there. But again, these are two very particular important strategies which are used in the field of networking, either go back and or selective repeat. Depending on what are your requirements, you use one of these strategies. So that's it for today. Today we have discussed two very important strategies, go back and selective repeat. So we have come one more further step in our discussion of TCP. Next lecture we'll start discussing the segment structure of TCP and see what additional informations we are required to incorporate in the TCP header. Remember, UDP header, we had a very small amount of information, 8 bytes of header. We'll see when we start discussing the TCP header, we'll see that many more informations are to be incorporated in the TCP header. So we'll start discussing the TCP header from next lecture. Also remember, all these discussions are based on your textbook, The Computer Networking, a Top-Down Approach, 7th edition by Jim Kurose and Ross. I also urge you to work on the examples or the exercises of this book to see whether you have understood the concept correctly or not. So till next time, thank you.